in terms of demo, just briefly explain what your goal was and what you ended up building and how you built it, and show us how it works?
Yeah, that sounds good. Do you want us to get started?
Yeah, that'd be great.
Okay, so our project is about Formula One tire degradation. For if you might not know, tire degradation is a big part of the Formula One sport. In that it's because a lot of times when the cars are going around the circuit, they're placing large amounts of cornering forces on the tires, a lot of G's on the car itself, which is transferred to the tires on the road. And as a result, the tires are known to blister either quickly, and a lot of times, tires sort of just explode in the middle of the race if the tires aren't managed well by the drivers by taking a more conservative driving line to the course. It's actually a very complicated part of the sport in that there's multiple different compounds that drivers can use during a race, that teams can use during a race to sort of that have different longevities and are expected to last different amounts of, race time. But what we wanted to implement was we wanted to analyze, existing Formula One data just from races and build a neural net that is capable of predicting, how much tire degradation are the tires going through with each successive lap for each driver. And that involved, collecting a variety of data and, building a neural net model and using PyTorch, and then implementing that neural net on the FPGA, and then driving, and then creating like a simulation of the race data that we have, and putting that simulation through the neural net to produce an output of what the tire degradation actually is. And I think Felipe can talk about the neural net that he built and the data that he collected to make it happen.
Yeah, so when I first came up with the project, ideally we were thinking of doing this with telemetry data, and what that is where you would see, for example, steering input, acceleration traces, braking traces, car speed, and then we were thinking like, oh, you could probably use all that data along with some history to then be able to try to estimate like the current tire condition. So like how much tire degradation has the tire already experienced based on what you're seeing with how the car is responding. But that's not data that we really have access to. So then we just went ahead and try to simplify the problem more. And then instead of trying to estimate the current tire condition, we try to estimate the tire degradation you'd see on a lot by lot basis. And then we went around looking for data, and then we ended up finding that website that had lap times available for each of the races. And then we decided to make a model around that. So then using whatever tires they were using, the track they were on, their lap times, to try to create some model to be able to estimate tire degradation. Now, there isn't a clear way to numerically say this is how much tire degradation is going on at any given point, but we still wanted to go through with this project as to be able to at least show that we can implement a neural net on the FPGA and show how that would work. So then I ended up just making an equation to try to approximate when the drivers would end up going to the pits based on their lap times, and along with some other factors having to do with the track conditions.
Okay. Can I just see, before you go on, can I just see if I'm understanding so far? So am I correct that there's a neural net that lives on the FPGA? The inputs will include lap times, the type of tire that the driver's using. Anything else that I'm missing?
Okay, so in our neural net, we decided to use a normalized version of lap time, which is per race. We have information about the track, so then how many slow corners, medium corners, and fast corners there are. And then those are also normalized based on all the tracks that we covered. Okay. For each of the 3 parameters. Then there is an input that is the expected tire life, which is based on what compound that is for a specific track. So with respect to that track, how long is it expected to last? That's also normalized across all of the races based on the different track compounds that are available. And then an additional factor as to whether or not there was rain at that given lap, because drivers will drive at different rates whether or not it's raining on the track, and also so then we try to take that into account both in when we're generating what we were expecting to see in the tire degradation, and also as one of the inputs that the neural net could see.
That's awesome. So some tracks are harder on tires than other tracks, and you take that into account in your model.
Yeah. So like again, like there is no clear way to be able to say like this is how much tire degradation happened on a lap by lap basis. Even if you try to look at the broadcast directly, there's no direct way to measure that. So I just made some equation to try to approximate that based on like when drivers would pit, and then tinkering around with like different constants and different manipulations of those variables.
Okay. Okay. Cool.
Yeah. So
Like-
then.
Oh, go ahead, Felipe.
Okay, so yeah, so then after like collecting all that data, putting it all together, I ended up splitting that into both into two sets of data primarily. There's the set that is just like those inputs that I just described for the neural net, so that those are already like normalized and they're ready to just be passed through the neural net, so then we could get some expected output. And then there's also the a different set of data, which is simulation data, which is what Rishi is going to use later to then like be able to display those races as we actually simulate them as we run through the inputs on the FPGA.
Now, in order to get all this data, did this live on a website somewhere?
So only the lap times themselves really lived on a website. The track information is based on the track layout itself. So then I can just look at an image and then like give values to those accordingly. The rain,
do all that, but you had to do,
the
you
rain
had
on-
to do all that.
yeah, and the rain on the rain on a lap by lap basis and the tire compounds that each driver was using each lap, I had to go ahead and look through previous race broadcasts to figure out what
Oh my
tires they were
God.
using,
That's
and then
so.
scrolling through different races and then being able to put all the information together.
So you built this up. A lot of this you guys built up yourself by looking at the races and.
Yeah.
Okay. Wow.
Yeah, so like the overall data set that we have, like we ended up just putting together like from different sources.
Okay.
Yeah, so then with all the data, then we had to go ahead and actually like decide what type of neural net we're making. At first like I was thinking it was like, oh, like we could do a convolutional neural network, but for this specific application, convolution doesn't really make sense because you're not really looking at global patterns and then more local patterns like you would with an image. So then instead we went ahead and did a fully connected neural network, which is just basically linear layers that go from the inputs, and then you have multiple hidden layers that every node connects to every other node from one layer to the next. And then it's just a matter of processing multiplications and additions from one layer to the next. And then to be able, even usually when you're trying to figure out how you're designing the number of layers and how big each layer is, you have to worry about how complex it is to not overfit the training data. But primarily wanted to test like how far could you push the limits of the FPGA. So then we ended up landing a size of 6 inputs from what I described before into a first hidden layer of 75 inputs, then down to a second hidden layer of 10 inputs, and then a single output at the very end.
Okay.
Yeah, and then we ended up building up the model in PyTorch, and with using PyTorch, and then there some training setup with different code, both from PyTorch, and then also had some reference code from one of my previous classes on how to train models using that. We ended up training the models to get the weights that we would use on the FPGA.
So you trained it in Python and got the weights and then implemented that trained model on the FPGA.
Yep.
Okay. Okay. Cool.
Yeah, and then Sujith can talk more about how the model itself was built on the FPGA.
So am I inferring then that the value add of the FPGA is here you could do it fast, and so it could be a real-time evaluation during a race, for instance? Is that the goal here? Is that?
That's what we were intending for, yeah.
Okay.
Yeah, so the idea, the much scaled up version of this project would be that the data that you would be using, it wouldn't just be the lab data, since that doesn't come in too often, right? Because it would just be like every minute and a half or so once you complete a lab. The idea is that you would be able to take in the telemetry data that you would have from the car and be able to evaluate those results real time. So then the idea is that you have to be able to run through a neural network very, very quickly to be able to keep those updates coming.
So the scaled up version of this could be a real-time race tool for the race teams.
Yeah.
Okay.
And in that scenario, we'd be looking at a different set of inputs, right? Sort of like what Felipe said, but they wouldn't be, I mean, we've sort of built a model reactively as opposed to just using the sort of data that would actually be kind of relevant for building a tire degradation model. We probably use things like braking effort, cornering forces, things of that nature to
Yeah,
build,
but
like, real-time
this sounds like
simulation.
a great proof of concept with the data that you have, right? I mean, you
Right.
built
Yeah.
what you could with what you have. Yeah.
Sure.
But yeah, so to build the neural net itself in the FPGA, we kind of had to parallelize development, so that because there was a lot of it to do, and we didn't quite know the size of the neural net till it was created, and we wouldn't know the weights of the neural net till pretty much like the last couple of days to go, really. So what we did was I decided to create a structure that would parallelize across the largest hidden layer inside the network. So this was a 75 node layer. And one of the real difficulties of implementing this neural net is handling all the weights that have to be sort of configured for each of the I guess the connections between the various nodes. And we got kind of lucky in that lab 2, we sort of implemented a streaming structure for reading out the initial conditions of the drum to the various modules on the FPGA. And we decided to use a similar structure where we would stream like a large majority of the weights to the various middle node layers to the widest layer, essentially. And the widest layer is then in charge of going about and computing each set of computation. And he would do that somewhat serially. And then once all that is done, the last layer or so just kind of happened on the very last step serially as well. And so all in all, we use something like, if I had something like 76, 77 multipliers. We could have gone for a more aggressive approach where we could have tried to use up like as many multipliers as possible, as early as possible. Then again, we didn't quite know what the exact structure of the neural net was going to be until later on. So we had to go for a more conservative approach. And simple, I guess, like even then, I think we were able to get data within something like 20 to 30 cycles. We were able to get a new output for what the tire degradation was. There wasn't too much emphasis placed on trying to speed it up as much as possible in this implementation, because then again, this is going to be a simulation, and no matter what, whatever output we're going to be shown is going to be slowed down by how fast the HPS is going to drive the inputs in, and we don't want to drive the inputs in too fast because you just be kind of jittery looking at it on a screen.
And I mean, 20 to 30 cycles at 50 megahertz is still definitely real time, particularly for human input type telemetry.
Yeah, and that's sort of what we're going for. And to sort of, I guess, coordinate the whole neural net, we just sort of relied on like a valid ready protocol between the HPS and the FPGA. So as soon as we raise we send a rising edge on a ready signal, the FPGA would just compute the value almost instantaneously, and we could sort of use that to display data on the next step. And I guess Rishi then put together, took this data and then kind of built like a terminal for this, really to depict the simulation as well as the tire data.
Yeah, I could talk about that. I'll share my screen while I do that. So we have like 2 displays here. We have the tire degradation on the monitor here, and this is where we're just going to plot it. Basically, the way our UI works is, let me start the program. So you can enter which race you want to follow. For this example, let's say we're doing the 70th annual. And basically, it's going to parse an Excel sheet of like the past race to get context and then give it to the user. So here you pick your driver. Let's pick driver 44. And it's going to show you which driver you picked. And now it's going to start displaying the race by a lap-to-lap basis. So every lap, it'll give you the tire degradation of the driver you're following. So I selected Ham, so you can see the previous tire degradation from the previous lap and all the current degradations for each driver. And meanwhile, like the tire degradations are being printed on the monitor here.
Fascinating.
And as you see, it kind of shot up there and it gave a little notification saying the driver took a pit stop. And so the degradation reset because now it's fresh tires.
Got tires replaced. Okay.
Yeah.
So this is, I don't have any intuition for this. How often during a race are tires replaced? Every few laps?
So the softest tires, I think they only last something like 15 to 20 laps maybe.
Wow.
Medium tires go on a lot longer, maybe 30 to 40. And I think hards, you should be able to last most of the race with them.
Yeah, it really depends on from racetrack to racetrack, and it depends what. So the tire providers, Pirelli, they end up choosing 3 different tire compounds, and they have a range, I think, of 5 in total they have available. It's like C1 through C5, where I think C1 is the softest and C5 is the hardest. I don't remember which direction it goes, but for each race, they'll select 3 different compounds as being the soft, medium, and hard for that race. And then in some races, the softest one for a 60 lap race could last maybe like 8 laps, or it could last like 15, 16. It really depends from one race to the next.
Wow.
Wow. And
Yeah, so
the horizontal line across the screen there, is that an indication of some sort of a threshold?
That's just 0. So 0%.
That's just 0. Okay. Okay.
Yeah.
Right. So like if you see, like there are a lot of values that are in the negative in the table. And part of that comes from when we were evaluating the tire degradation, we were, instead of thinking in terms of what's the limit that the tire can take before it just gives out and explodes. So that's really hard to measure because you don't really get that information because drivers don't drive until their tires explode.
Mm-hmm.
Simple as that. So then our reference point was more towards when do drivers typically pit when they're using these tires. So then when you see these values going more towards the negative, it's an indication they're trying to make their lives, they're just driving on their tires longer, even though that typically they would be expected to pit, they're still trying to drive longer on it. And it could be just because of strategy or because the drivers still feel like their tires are holding out better than our data suggests.
But if this were a real-time tool and those values started going negative, you could imagine something like a red light flashing saying pit, 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 something like that.
Right.
Some indication that's like
Or you should go take a
your
pit
tire
stop,
condition
yeah.
is significantly worse. You should be expecting that you're losing time per lap at this point, and then you should probably change tires.
Okay. So this race just completed. Do I interpret this correctly that this driver pitted twice?
Yeah, that's correct.
Okay.
Yeah. And I'll just show you like 2 other cases too. We also explain if there is rain or not in the specific lap.
Mm-hmm.
So, for example,
does rain make degradation worse or not worse?
So if you're on
like
normal
these laps,
tires
it's
and you're
raining.
trying to drive in the rain, a lot of times you'll see if you try to drive just as fast or like at a similar speed, usually you'd see more tire degradation just because you usually don't have as much traction on the track, and then like your tires are gonna slip more.
Okay.
So then that's usually gonna hurt your tire degradation. But because usually you're forced to go significantly slower compared to the rate you normally would, the tire degradation isn't necessarily that different, but compared to with respect to how fast you're going, that you would see a similar amount of tire degradation from like in the end. But like that's if you adjust the time because of the fact that it's raining, you end up going slower.
Yeah.
But dealing with that loss of traction and then like considering that like drivers won't necessarily drive perfectly and then they'll slip more, that you might end up seeing more tire degradation. And the tires won't last as long.
It's really interesting.
And these laps, there's no rain, so it stopped displaying that.
So there was a pit.
What's the little glitch at the just after the start where it dropped and then came back up again?
Oh, I think he took an early pit in that part.
Yeah, so
pretty
in
close.
this race in particular, I think it was raining for maybe like the first, or else it had already stopped raining at the very beginning of the race, but the track was still wet for the first 3 or so laps. So the drivers were on wet tires. Well, specifically intermediate tires, but they're tires made for when the track is wet, just to have better traction.
So that when it started to dry out, they changed to better tires.
Yeah.
Yeah.
Can they switch tire compounds during the race? Like, can they go from hard to soft, and that is allowed?
Yeah. So actually, they're required, if the race is dry, they're required to use 2 different compounds throughout the race.
Interesting. Okay.
And there's usually a lot of strategy as to when to throw on different compounds. Like soft compounds are, definitely much faster than using like a hard compound, but soft compounds like rip much faster. So you know, if you're a front runner, you might use like the soft compounds to get to the front of the race, front of the pack, and then you know once they start to die, throw on like hard compounds or medium to kind of get you to the end of the race. While other teams who are like middle or back pack teams might you know use different strategies to get them through the race, while also giving you know using different opportunities during the race to kind of get ahead, while other teams are on slower tires.
It's so interesting.
Well, you all seem to know a lot about Formula One. Is that is this what you do in your spare time?
Yeah, I'd say at least for me and Felipe, yeah.
Yeah, to some extent, yeah. But I think also looking through all this data for quite a while also helped.
I'm sure.
I can't believe you guys built up this data set. That's awesome.
Yeah, one of the limitations that is in this model is that in making the labeling for the tire degradation that's expected from the neural net was that I don't really take into account the lap count, and that would be pretty important in the real world because you burn off fuel, and in Formula One you're not allowed to refuel. So the car is significantly heavier towards the beginning of the race, and then as the race goes on, the car becomes lighter. And since the car is lighter, it's not really going to put as much stress on the tires. So then you would actually expect to see the tire degradation decreasing throughout the race. But that's not one of the things I take into account when I was making the labeling. So then you don't really see that.
Okay. Can you explain the data path for me one more time? Because you said this is parsing an Excel sheet, correct?
That's right. So it's parsing an Excel sheet for the beginning just to get context. So things like who are the drivers, what is the lap number, and what is the time each lap.
Okay.
And then the tire degradation comes from the FPGA itself.
Right. Okay.
Because we're sending like the inputs. The inputs also like all the weights that we have, that's initially like, you know, it's a pre-computed model. So like we take the inputs and weights from the Excel sheet, parse that in, and then send it to the FPGA and then get the tire degradation out of it.
And I see here that you're even accounting for, this looks like a corner case where this driver did not finish the race.
Right.
And your system accounts for that. Okay. Wow. Really cool.
Yeah. So you're gonna pitch this to a team?
And I think there's a lot of good bones to this project, and you know it shows that a lot of proof of concept. But I think you know really it'd be awesome if the team gave us this telemetry data and then redo it with an actual data set.
It'd be really interesting to see what you could come up with that kind of data. Yeah. Yeah.
Yeah, because and then at that point, you would probably convert from this being a standard feed-forward neural network to being a recurrent neural network, which is basically like the nodes, they have some recollection of what the previous values that they've seen were, and then based on those previous values, you're also able to change your output. So then, like, we'd probably have to do something along those lines if that were the case.
Okay.
Cool.
Really cool. Thank you, guys.
Thank you.